Hi, my name is Erik, and today I'm going to talk about how to use the Euler characteristic to measure shape in biology using a small collection of Python scripts that I have named demeter. So the brief outline is to give you a gentle introduction to the Euler characteristic in case you are not familiar with it, and focus on the Euler characteristic transform, which is what actually goes behind the meter, and see this in a couple of examples for both 2D and 3D images. This is also meant to give you a place to start. You can grab these same tutorial and slides from this GitHub repo. So most of the research that is being carried in my lab and the main inspiration behind the meter is plant biology, especially because in the plant biology building here at Michigan State, we have an X-ray CT scan machine where we have thrown in all kinds of flowers, fruits, shoots, roots, leaves. And we have these extremely detailed and very large X-ray CT scans where we can simply wonder, how do we even begin to measure these intricate and complex internal structures and vasculatures in a very comprehensive and robust way? So to do that, my lab also focuses on topological data analysis, TDA for short, which goes with the motto shape is data and data is shape. And the whole idea of TDA is that you start with some raw data and with some object, and with a mathematical framework, you extract a series of numbers, a sequence of numbers that summarize shape, mathematically speaking. And once you have these numbers, then you do a standard analysis and machine learning. And the point of today is to understand how do we go from shape, a subjective term, to these numbers using the Euler characteristic. And you can also check more details on TDA in our 2020 review. Now, to think like TDA, we need to first think in terms of topological objects. Our image is a topological object, meaning a cubical complex that is a collection of vertices, edges, squares, and cubes. And the whole goal of TDA is that we are going to describe the shape of our image and based on the topological features of its associated cubical complex. In this case, features like connected components, which are, in this case, the blue and the red things, two separate things. Loops, like the square frame you see over here. Notice that these squares are not loops because there's a square, an actual tile blocking the loop, and voids. This is in 2D, so we are not going to see voids in this case. But whenever you are looking at X-ray CT scans, images are massive, so that means massive cubical complexes, and even keeping track of these three things can be quite a challenge. So we go one step even further, and that is you take a topological summary based on the Euler characteristic. The Euler characteristic is a topological invariant, which is simply the number of vertices minus the number of edges plus the number of faces. So for those who are not aware of, if you have these platonic solids, you always get the number 2 by doing vertices minus edges plus faces, which is not surprising because all of these objects are topologically equivalent to a sphere. What is surprising is that the Euler characteristic is deeply embedded in the features I just mentioned, which is connected components minus number of loops plus number of voids. And just to give you a quick rundown, each of these platonic solids is one connected component, one single thing. There are no loops, there are always tiles, and assuming that they are hollow, that's one void. So that also gives you the number 2. Now, the Euler characteristic on its own might be too simple. It cannot distinguish a cube from a pyramid. However, we can pick a direction, say top to bottom, and slice our shape, in this case a barley seed, and you slice the seed across that direction. And as you slice the seed, you keep track of how the Euler characteristic changes. The number of slices, or also known as the number of thresholds, will tell you how much information you pick as the Euler of how the Euler characteristic evolves or changes as you slice. How do you pick the best direction? You actually don't. You go with all possible directions, and that is the Euler characteristic transform. So in this case, pick 3 directions, all possible directions. That's actually infinite. We cannot plot that. But for practical purposes, let's imagine that there are only 3. In this case, red, blue, and green axis. And You pick these three directions, you chop the seed across those three directions. That gives you three different ways on how the Euler characteristic changes. And by the end of the day, the Euler characteristic transform simply concatenates all of these in a single thing. So this is the Euler characteristic transform. The cool thing of the Euler characteristic transform is twofold. Computationally speaking, it's just the number of vertices, edges, faces, and cubes, so it's extremely efficient. And mathematically speaking, if you take all directions or a very large amount of directions, you can actually mathematically prove that all there is to know about shape, it's captured by this Euler characteristic transform. Now, finally, let's see some examples. So in this case, everything is based on Python. So we have our standard libraries, NumPy, Panda, SciPy. What is new, our contribution here is the demeter, which again, you can grab it from the GitHub repository, and submodules to compute the Euler characteristic, the directional filters, and some miscellaneous. First step, you load the data. Let's go with the simplest case, a binary to the image, in this case, a fern leaf. We load the data, assuming that it's a NumPy array. We need to complexify it, and here is where things come into play. So define it as a cubical complex, complexify it, and done. So we have vertices, edges, and squares for our. So we went from a binary image to a collection of vertices, edges, and squares, a cubical complex. Choose directions. So let's pick regular directions in 2 dimensions, the dimensions of the leaf. Let's pick 24 directions spread across the circle, spread regularly across the circle, as you can see here. So those are 24 directional filters. And let's compute the Euler characteristic. So we have a cubical complex, and we have this associated function, the Euler characteristic curve, that takes a filtration and a number of slices. And that's exactly what you are seeing here, which in this case, we have a fern leaf, and we pick a filter, which in this case, it corresponds to a direction that goes from southwest to northeast. We can vary the number of slices, and as you can see, as we vary the number of slices, we can pick more shape nuances. And as advertised, the Euler characteristic transform is nothing but the concatenation of a lot of these Euler characteristic curves corresponding to different directions. So different directions will give us different kinds of glimpses, different glimpses of how shape changes. And by taking all together, we have the whole information of the fern leaf. It's worth noticing that computing this Euler characteristic transform for about 65,000 vertices took us just a fraction of a second. So pretty versatile there. Also, as advertised, this same thing runs with 3D data, like a barley seed. So without changing anything, we go with a seed image, we complexify it. And in this case, because it's 3D, we have vertices, edges, squares, and we have cubes. This is very ad hoc. For this seed, we just rotate it, and we can also plot it in 3D to make sure that it's actually a seed. Pick regular directions. By default, we go with always 3 dimensions. So in 3D, pick 128 points regularly spaced. We can also plot that sphere to actually verify that they are evenly spread. And just as before, we have the Euler characteristic curves for the seed. So one direction and different number of threshold, different number of slices, picks up different nuances. And also notice that there's also some point where it doesn't make much of a difference how many thresholds you pick. There's not that much nuance difference. Even here, you already have the basic shape. However, again, not you don't focus on one direction, but you focus on multiple directions, in this case, 128 directions, and you slice the seed 16 times across each direction. That gives you a massive vector of almost dimension 2000, which again, it's computed in a pretty decent, in an acceptable time, considering the number of voxels or 3D pixels. Also, we are not just limited to directional filters. Say instead of a binary image, we have an actual grayscale and actual X-ray CT scan. That's what I've been mentioning since the very beginning. We have an X-ray CT scan of an orange. Now, keep in mind that it's notice that this orange is just a circle. So topologically speaking, there's not that much information we can actually gain no matter what direction we pick. But in any case, so first we complexify it. So vertices, edges, and squares. So by virtue of being a circle, we don't have that much information, but we can also pick as our filter, instead of directions, we pick density value. And by doing density value, then we get a bit more of interesting shapes, interesting information regarding shape with the Euler characteristic. This is the Euler characteristic transform. Doing directions, yeah, there's pretty not much to say out here, but densities actually gives you cool information worth taking into account. So now that you have converted shape into numbers, then again, you can go to do standard analysis and statistics. Thanks to all the organizers for being here. I'm happy to answer more questions later.